Hello my dudes, and welcome back to Viewfinder Engineering. Today we're going to be calculating gain and phase two ways, using Euler's method and transfer functions. Gain and phase are part of the particular solution to our system differential equation. Now, they are dependent on the input, unlike our homogeneous solution. And they are key players in our good friend frequency response, so like sinusoidal inputs. Gain is the ratio between our input amplitude and our output amplitude. It's basically how much of a response you're going to get per unit of input. Now, the phase shift is the angle that the output is going to lag or lead by. A negative phase shift means that the output is going to lag behind the input, but a positive phase shift means that the output is going to be in front of the input. Now, this isn't quite as common for our applications, at least that I've seen. I mean, it does exist, like we used it in electrical engineering, but for the sake of today, we're just going to assume that our phase is going to lag. And that lag is going to tell us how big of a delay there is between the system receiving the input and yielding the output. Now that we've covered the basics, let's get into some calculations. But before we do that, let's pause really quick. So here's the thing. There are two ways to do these calculations. Both are equally valid, but I just really prefer the transfer function method. I'll walk us through the Euler method derivation, but it just really doesn't make sense in my brain. So if you just want to skip to some glorious transfer functions, the timestamp will be here somewhere. Alright, let's talk about our good homie Euler. He's got this thing called the Euler Identity, and here we're going to be using it to be converting between polar and rectangular coordinates in the complex plane. So in this equation, the e to the j omega t piece is our complex vector that is denoted using sine and cosine. Using this, we can find the magnitude of A to find the amplitude of the output, and the angle of A to find the phase shift of the output. So, let's consider the system mv dot plus vv equals f naught sine omega t for this derivation. Now, the first thing to note is that we've assumed this input is sinusoidal, with the generic frequency omega. Having a generic frequency is key for finding our gain and phase, but once we have our generic solution, we can go back in and plug any number of frequencies in. We start by taking the imaginary pieces of our output and input. Now, using Euler's identity, we know that we can rewrite our sinusoidal pieces in this form. And if you need proof, because all of this looks like witchcraft, at me, we can sanity check ourselves by matching our input to our Euler identity. So if you notice, the imaginary piece of this is the sinusoidal input, and the imaginary piece of this is also the sinusoidal input. It's the same, it checks out. The only difference is this little j value, and that's just going to denote our direction in the complex plane, so we don't really need to worry that it's different. Yay. So to finish up step one, we can just take a look at our output here and notice that the same thing applies. However, in this case we have our placeholder amplitude h, and that's because we haven't solved the equation yet, so we don't know what this value is going to be. But we're going to be using this value in calculating our gain and phase. And the reason we can even apply our Euler identity here is because we know that by feeding a sinusoidal input into the system, our particular solution is going to be a sinusoidal output. So moving on to step two, we need to take all the necessary derivatives of v to fill in our equation. So in this case, we need to find our v dot. Now, it's important to note that in this case, the system is first order, so we only need to take v dot. However, this method extends to higher order systems too. You just gotta take more derivatives. Okay, for step 3, we now need to take all of our Euler's identity pieces we just found and plug them back into our original equation. Then we can coefficient match to find the value of h. Now, as you can see, the nasty stuff is going to cancel out. And we can now solve for h in terms of our input and our characteristic equation coefficients. We almost there, guys. I promise. So next we want to find the magnitude and the angles of this term h, and we can do that as such. Now, if you remember from our Euler identity, we established that j was just a component indicator, so it's not going to go into our amplitude. Now, there's one last step before we can find our gain. We have to normalize our output by our input. So it's been a long time coming, but we finally have our gain. Now let's calculate phase shift. We can take the angle of h to find the output angle, or the phase shift. We take the arctangent of the numerator and subtract out the arctangent of the denominator, like so, and boom, phase shift acquired. That was cringy. So, step 1, we took the imaginary components of our input and output using Euler's identity. In step 2, we took all of our necessary derivatives in order to fill in our original equation. So in this case, we only had a v dot, but this could potentially go into higher order systems. If you go into systems where we have derivatives of our input, you know, the possibilities are endless. In step 3, we coefficient matched with the imaginary pieces of our equation to solve for h. And last but not least, we normalized the magnitude of h by the input to find gain, and took the angle of h to find our phase shift. So I think we all can agree that was gross, but fear not, my dudes, there is an easier way to do this. Enter the transfer function method. Let's start with the same system that we used in our last example. However, instead of calling up our buddy Euler, let's look to Laplace this time. For step 1, we start by converting this equation into the Laplace domain. In step 2, we are going to rearrange our variables to get us a good transfer function. Now, remember that our transfer function relates a single output to a single input. So in this case, v of s to f0 of s. For step 3, we're going to evaluate our transfer function at j omega. Why? Magic. To do this, we're just going to plug in a j omega everywhere we have an s. Now, the beauty here is that we're basically done. I mean, kind of. To find the gain, we just take the magnitude of this transfer function, and to find the phase shift, we just take the angle of the numerator and subtract the angle of the denominator. Now, as we saw with Euler's method, the j here cancels out because it's just a component indicator. And again, we see with phase that we take our numerator minus our denominator, and we find the angle by taking the imaginary components over the real components. So to wrap up this derivation, we can take our gain and phase and plug it back in to find our particular solution. So, just like in our Euler example, we find that v of t is equal to our input amplitude times our gain times our input frequency plus our phase shift. And again, the phase shift is negative in this example because the output lags behind the input. Easy, breezy, beautiful transfer functions. So just to solidify all this in our brains, let's walk through the steps one more time. In step 1, we took the Laplace transform of our system equation. In step 2, we rearranged our variables to give us a transfer function. In step 3, we evaluated our transfer function at j omega by replacing all the s's with j omegas. Finally, we took the magnitude of our transfer function to find the gain, and we subtracted the denominator angle from the numerator angle of our transfer function to find phase. And remember, these angles are found by doing the arctangent of the imaginary components over the real components. Now, because I love transfer functions so much, let's raise the stakes a little. Try something a little bit spicier, second order perhaps? Just a quick little example before we wrap everything up. So let's say we were given the system x double dot plus 25x equals u of t, where u of t is a sinusoidal input. We start by putting it all in the Laplace domain. So s squared x of s plus 25x of s equals u of s. Next, we rearrange this to get our transfer function. Then we can evaluate this at j omega. Now, in this example, it's important to note that our j is being squared, so it turns into -1. Now, from this, we can use our handy-dandy formulas to find gain and phase. So, remembering that the gain is the magnitude of our transfer function, we find that the gain is 1 over 25 minus omega squared. Since our j took care of itself earlier in this process, becoming a negative sign, we don't have to take the square root, because this is already the magnitude. Now, remembering that our phase is the angle of the numerator minus the angle of the denominator, we find that we actually have a phase shift of 0 degrees. This is because we don't have an imaginary component to our numerator or our denominator, so both angles go to 0. So just like that, we have our gain and our phase. Super easy, super quick, simple to remember on tests, 10 out of 10, 2 thumbs up from me. So there you have it. 2 different methods for calculating gain and phase. In case you couldn't tell, I am a transfer function gal myself, but honestly, you do you. Follow your dreams. And let me know down in the comments if you're Team Laplace or Team Euler. Is that reference old? Am I dating myself by making that joke? YOLO, whatever. Thank you so much for watching. Be sure to give this video a big thumbs up, especially if it helped, and to hit that subscribe button for more content about college level math, and engineering, and science, and all that jazz. Okay, bye!